Hey guys, hello and welcome back to my channel. This is Kshitij, and on this channel we talk about robotics, research and academia. This is the fourth lecture of TT101 Basics of Mobile Robotics lecture series. In case if you have missed the previous lectures, the link will be in the I button above and the entire playlist will be linked in the description box below. In the playlist, all the lectures are chronologically arranged for your convenience. So in today's lecture, we will take a quick recap over what we learned the last time. What can the sensors do? Interoceptive and exteroceptive sensors, some characterization, some mathematical analysis of how you define the performance of a sensor, and the challenges that the sensors present for mobile robots. So let's get to it. First things first. What did we learn the last time? So last time in the previous lecture, we looked at preliminaries and notations. We looked at reference frames, transformations, undoing transformations, some motion constraints. And today we are looking at sensors for mobile robots. In the last lecture, I had already covered that sensors could be exteroceptive or interoceptive, where the exteroceptive sensors can also be active or passive, depending on whether they emit energy or just observe ambient energy. So now the obvious question you might have is, what can sensors do? So to answer this question, think about the 5 senses that you have as a human being: the sense of sight, smell, touch, taste, and hearing. Now, we might not be going into the sense of taste for mobile robots, but the other senses are very relevant, and you will quickly start to see similarities between the senses we discuss and these 5 sensing modalities that we have as human. So in a sense, typically what we do with the senses is to gather information, and that is exactly what the robot does as well. So it tries to understand what is around it and where it is operating, because oftentimes when we deploy a robot in an environment, a large part of it is unknown. We don't know what adversaries are there, if any, what the environment looks like, is there any structure in the environment. Things are even challenging if you're deploying a robot post a disaster site where everything has kind of collapsed and crumbled, so there is not much of a structure anyways. So these sensors help the robot convert a physical phenomena into a real valued output signal, which you also call as an observation or a measurement, which could be something like light intensity, scene occupancy. So it could be binary, such as saying whether a certain area in the environment is occupied or empty. Occupied could be occupied by an adversary, occupied could be occupied by a static obstacle, etc. And something about operational conditions, where what the terrain elevation is like, are there any wind gusts, etc., which affect the navigation of a robot. For instance, if a drone is trying to go upstream, so against the wind flow, and it might incur large amounts of energy to get to the point where it is going, and so on and so forth. So that's why you need sensors for environmental awareness. And this awareness is not just with respect to the conditions you're operating in, but it could also be in terms of, are there other robots in the environment? Are those friendlies or adversaries, etc. So now we start looking into interoceptive sensors. And remember, interoceptive sensors, we have already done a high-level overview in the preliminaries. In case if you have missed that lecture, the link will be in the I button above. So the first interoceptive sensor we're going to look into is an odometer. So this is one of the very commonly used self-awareness sensor on a mobile robot. And it helps measure how far the wheel has moved. From, let's say you're starting at t equals to 0 from a start position, and it will, as the wheel moves and rotates, it will then give you a rough estimate of how far the wheel has moved. To some extent, this is the same as dead reckoning or path integration. If you come from other domains, you might have heard those terms already. So the way it works is it encodes the rotation of a shaft or an axle. So what you see on the left is a disc, and in the middle is a hole, which is basically then used to mount this disc on a shaft or an axle. And as the axle rotates, this disc rotates. And this disc could be one of 2 types. So one is this slotted disc that is shown here. And this works on the principle of brake beam shaft encoding, which basically is working as such. So your LED is emitting some light, and through the slot, the light goes and falls on a photo sensor, but when there is a blockage between the two slots, the light is blocked and the beam is broken. So your photo sensor is then measuring how many slots have you crossed, and that gives you the amount of rotation you have done so far. Another way of doing this is, instead of having a slotted disk, you have colored disk, where you could imagine it to be sliced up like a pizza slice. So you have multiple slices, and each slice would take up different color schemes. And then you're measuring the reflectance based on that, and using the colored disk as opposed to a slotted disk. So that's your odometry. Then a pop quiz for you is, can the shaft encoding principle be extended to not only just measure the distance you have moved so far in terms of the amount of wheel rotations? So imagine that if you know the radius of the wheel and you know the amount you've rotated, you can easily convert that to the distance. But what if you could also know the direction of motion? So it could be in terms of forward, backward, or clockwise, anti-clockwise, so relative direction of motion. But can this principle be extended? So here's a bit of a spoiler. You want to check quadrature encoders, and then you will get the answer to this pop quiz. And as always, once you have the answer to the pop quiz and you want to answer the pop quiz, you go down to the comment section below, mention the number of the pop quiz. So in this case, it would be pop quiz 4.1, and then put in your answer, which you think answers the question. It's the same logic for all the pop quizzes throughout the lecture series. Next interoceptive sensor we are going to be looking at is an accelerometer, which measures the inertia when a mass, in our case a robot, undergoes a change in velocity. Now, one caveat here is that acceleration measures the g-force and not the acceleration in terms of rate of change of velocity, as the name would otherwise suggest. So it could measure roll, pitch, and then the downward gravity, but it cannot measure yaw. And as you know, if you double integrate acceleration, you get an estimate of your position. So that's why we use accelerometers to convert inertia into some rough estimate of the position of the robot. Then a magnetometer. So it's a 3-axis magnetometer in this case, and it's just an example device with the chip that I've taken here. Could be of different kinds. But it, as the name suggests, it detects a magnetic field, both the strength and the orientation near an object where you're placing the magnetometer. And it could be operating in one of two modes. One is it could give you the relative heading. So for instance, if you know your last bearing or heading, and if you take the current bearing or heading, you could kind of evaluate how much difference do you have from the current bearing to the last bearing. So you are relatively checking if you're still on course or if you have drifted away. And then there could be an absolute heading, which is basically calibrated with respect to some internal constants of the material that is being used to design the magnetometer, and it gives you the absolute heading as opposed to with respect to the previous heading at t-1. Next up is a gyroscope. So it's a 3-axis gyroscope, and in the preliminaries we have talked about the gimbal lock problem. And if you are into video content creation, you would know the gimbal that is commonly used to stabilize your video device. So it's working on the same principle, and it could be operated in one of two modes. So there's a mechanical gyroscope, which gives you an absolute measure of the heading of the robot, so you get an understanding of the orientation. And then there is a rate gyroscope, which gives you angular speed. So it just gives you the rate of change and not the exact orientation. And it maintains an orientation with respect to a fixed frame. So remember that we talked about frames of references in the preliminaries. So there would be a fixed frame, and with respect to that, you get to maintain orientation. And if you integrate the velocity in terms of degrees per second, you get an instantaneous angle. So you can go from rate to an angle. That's the purpose of having a gyroscope, to understand the orientation. Now, there is also this interoceptive sensor called an inertial measurement unit. So each of these previous 3 sensors that we looked into, the accelerometer, magnetometer, and gyroscope, they all have their respective noise issues. So most of your measurements are just going to be estimates, because you're going to be doing integration or double integration to get an understanding of your position or orientation. There would be drift. So for example, magnetometer is affected by the magnetic field of other objects around you. So your microwave oven is a very strong magnet. Your mobile phone has a magnet. So a lot of these electronic devices have magnetic components on them. So there would be interference amongst them. So there would be a lot of drift in such cases. So to overcome these kind of challenges, we normally try to use multiple of these sensors and try and minimize the impact of errors from individual sensors. We will look into sensor fusion in one of the later lectures, but this is essentially what an IMU does. So it fuses at least two of these three sensors. So it could have a 3-axis gyroscope and a 3-axis accelerometer, which gives you 6 degrees of freedom. And it could give you an absolute measurement of roll, pitch, and yaw, but only an estimate of the position in XYZ coordinates in the 3D frame. Additionally, you could add a magnetometer on top of that. So you would have a gyroscope, an accelerometer, and a magnetometer, which gives you 9 degrees of freedom altogether. So a question for you is, do you think 9 degrees of freedom makes your life easy? And because you have so many degrees of freedom, you would get like absolute amazing readings for position and orientation? Or are there going to be some challenges if you have 9 degrees of freedom? This is essentially what this Pop Quiz 4.2 is asking you. Okay, now with interoceptive sensors out of the way, you have an understanding of what's happening on the robot, right? So you have position, orientation, these kind of measurements taken care of. Now we start looking into exteroceptive sensors, which is going to give you some insights into the environment around you. So we're going to be looking at both passive and active exteroceptive sensors, and most of them have similar working principle. They are trying to estimate distance for you to some extent. And the way it works is, for active sensors, they will emit a packet of energy, which we saw in the preliminaries as well. And that bounces off some obstacles into the environment, and then it's reflected back. And that, based on working principles such as time of flight and received signal strength, you could evaluate the distance. Now, a couple of things to take note here. Note that how I have shown the reflected energy as a bit smaller than the emitted energy. This is not a typo. This is done on purpose. The reason being, when you emit the energy, the intensity would get attenuated, because when it bounces off an obstacle, some of the energy might be refracted, some of it might just be absorbed by the obstacle. So the amount of intensity that you get back is not going to be identical to the amount of energy you emitted. And if you know this attenuation model, then you could use what is known as the inverse square law to understand the received signal strength from the signal source. So for instance, you are standing a certain distance away from your Wi-Fi router, which is the one generating your Wi-Fi signal. And if you know the distance, then you can understand what would be the received signal strength of the Wi-Fi at your location, which is a certain distance away, by using this inverse square law, which says the amount of signal attenuation is inversely proportional to the square of distance from the source. So if you are 5 units away from the source and you know this attenuation model, you can understand what proportion of the energy would you be receiving at your location. Time of flight, on the other hand, is basically as the name suggests. So you emit certain energy, it comes back. So when you emit, you start the timer. When it comes back, you stop the timer. So you have the time of flight. You have an assumption on the travel speed of the signal. So if the signal is traveling through air, through water, through some other medium, you have an assumption of that. And then you try and evaluate, okay, how far would an object be? Because you know the speed, you know the time, so you can calculate the distance. One thing to note here is that because the timer takes into account a round trip, which means that the signal was emitted and the signal was received, but you only want the halfway distance because it's covered twice. So you would have half of the velocity times time. That's just, I think it's very simple physics. So that needs to be taken care of. And typically with these two working principles, we're able to estimate distance using most of the active sensors. So let's start looking at them one at a time. The first active sensor for measuring distance using the receive signal strength principle is an infrared proximity sensor. And as the name suggests, it uses infrared light, which is the emitted energy in this case, which is invisible to human eye. And the emitter is an LED, which emits an infrared light, and the receiver is a photodiode or a phototransistor, which receives the infrared light when it bounces off an obstacle, and then you evaluate the received signal strength to evaluate how far were the obstacles which reflected the infrared light. And now this is a very cheap sensor. You could use it easily for hobby robotics or education robots, and the reflective intensity depends on the object characteristics. So for instance, if the object is smooth, you might get back a lot more of your infrared light when it reflects, as opposed to a rough surface, which is going to scatter it all around. So you'll have a lot more attenuation. Then different colors of the object would have different absorbing and reflective properties. So you need to take that into account when you're using sensors like this. Another distance measurement sensor is an ultrasonic sensor. So this is similar to how you would, let's say, use your ears to figure out how far an object is. So the only difference is your ears are not emitting audio, they're just receiving and then trying to understand how far is the source of the audio. But the working principle of this is that it emits an ultrasonic chirp, and hence the name. And this again is inaudible to humans. And like I said, for the time of flight principle, so you start the timer as soon as you emit the chirp, and then when you receive the chirp, you end the timer, and then you evaluate the round trip time of flight, and you do the half of velocity times time to get the estimated distance. Now, the emitter in this case is a transducer. Now, transducer is a mechanical principle which converts energy from one form, which is mechanical, to an electrical form. So here you're going to have a mechanical membrane similar to your eardrum, and it would then, based on the flexing of the mechanical membrane, it would then be converted into sound, and your receiver obviously is going to be a microphone which then hears the sound. This is commonly used by the ships. So when you're navigating, you send ultrasonic waves to map out the surface under the water. And if you've seen some Discovery documentaries, or if you've done some Loch Ness Monster trips kind of cruises, then you could go into the captain's cabin and you could see the map on the screen. Those are ultrasonic maps. And the question for you is, all this sounds amazing in principle, but do you see any challenges with emitting these kind of sonar sensors, or ultrasonic sensors as they're called? So they emit ultrasonic chirps, and then based on the round trip time of flight, they estimate the distance. Do you see any challenges with using a sensor like this? And if so, what are those? Next up is a laser scanner, often sometimes interchangeably known as a LiDAR, where LiDAR stands for light detection and ranging. So the way this works is it emits pulse of light and measures the time of flight. And often it uses coherent light, which is infrared in nature. So again, not visible to the human eye, and coherent means the light beams would be of the same wavelength and same phase. So they would not be offset, which means you're going to get a very concentrated narrow beam. And it uses rotating mirrors to increase the field of view. So then you basically have a way to spread around your laser beam across the environment. And it is commonly used for high-end robots, let's say for autonomous cars. And it has a very high sampling rate, but it's very expensive. Hence, it's used for high-end robots. And it could operate in 2D or 3D. And there is also a cheaper version of these. So for example, the LiDAR that you see here is a Velodyne LiDAR, which is very expensive and often used for high-end robots. Could be like the robot dog, or could be autonomous cars, etc. But there's also cheaper versions of these sensors, which could operate, let's say, in 2D, which could be something like a Hokuyo LiDAR, another manufacturer that are a bit on the lower side. So there are different kind of laser scanners and LiDARs out there, and they could work in 2D or 3D. Now, caveat here is that although people like to use the word laser scanner and LiDAR interchangeably, You need to understand that laser scanner is a device, but LiDAR is a technique. So remember, I called it light detection and ranging. So this is a technique or a process, and it is used by a laser scanner, which then uses laser beams for detecting objects. So this is a slight difference, but often people tend to use the terms interchangeably, but you might want to take note of this. Now, the brain teaser for you here is that consider a hobby mobile robot with a 2D laser scanner. So we're talking about, let's say, a cheap end laser scanner. And these are the laser beams sent out by the 2D laser scanner in a plane, which we call as the sensing cone. So let's say this is something like a 210-degree sensing radius, and within a 2D plane, you have a coverage of 210 degrees in front of you. And the question for you is, what are the challenges you foresee when using an environment in 2D laser scanner for indoor environments? And just to give you some food for thought, you could think about deploying a robot like this in an indoor environment which has obstacles such as clear glass partitions, has tables like this, so it could be tables and chairs with legs, which a lot of empty space between them, and could even have staircases. So imagine your robot starts off here at the top staircase, and you have only a 2D laser scanner. Let's say, for the sake of simplicity, you don't have a camera. So if you had a sensor like this with a sensing cone like this, and you had these kind of objects in your environment, what challenges do you see when you're using a 2D laser scanner? Comment down below and let me know what you think. And these are just some examples to get you to start thinking, but there could be other examples where you might face certain challenges. And this is just like a subtle hint to get you started along these lines. But yeah, feel free to expand upon this idea and discuss all about the challenges of 2D laser scanners for indoor environment. And another very commonly used exteroceptive sensor is a camera. It could range from a very cheap off-the-shelf USB web camera to very expensive high-end cameras, because you can get a rich stream of information from the environment, which is inherently very complex. But the good thing is vision in humans is very well understood. Over the years, we have studied quite a bit, all the way from neuroscience aspects to how the brain processes things. So the entire perceptual pipeline has been studied across the stages. And the way vision works typically is that you try to take a 2D snapshot of a 3D world, unless there are certain extended cameras which give you more information than a 2D snapshot, and we'll talk about them in just a moment. But this is how we got started. So you try and simplify what you see, and it's more like a projection of the 3D world onto a 2D plane, and then you try and reason about it. The good thing is, as I was saying, so most of these cameras are available off the shelf, they're cheap, and the entire perceptual pipeline, all the blocks have been standardized to some extent. So even if you want to deploy some algorithms to process your data, to clean up your data, to make sense of your data, everything is out there. You could just use the open source tools on the software side, and also the hardware side is readily available. So that's why it's becoming a go-to sensor. One caveat, though, is most of these cameras would get affected by sudden illumination changes. So imagine yourself when you go from a dark room to sudden bright conditions, or when you go from bright conditions to, let's say, a cave-like environment. Even your own eyes struggle a bit to adjust to sudden lighting changes. So the same things apply to the camera as well. And the way typically a camera sees the environment is, this is an image of Abraham Lincoln, and forget whether it is grayscale or color images, etc. We'll discuss the perceptual pipeline in a later lecture, but for the sake of argument, this is basically, you have a face in 3D that gets scanned in 2D, so that's an image. But the way your camera sees it is typically a matrix with a bunch of numbers, and these numbers are light intensities, where the image is discretized into what we call as pixels. So each pixel here is then denoting the light intensity. And the way cameras work is you have different resolutions, meaning the number of grid cells you get in an image could vary. The more you have, the more finer pixel you can have control over. Otherwise, your image would be very, very coarse, and so on. As I was saying, so not just this, there are very high-end cameras these days as well. So panoramic cameras are being increasingly used in VR, virtual reality, and augmented reality applications, which give you like a full 360-degree panoramic view of the environment. So you could mount that on a stick and have it on a robot. So telepresence robots and these kind of applications are using these cameras quite a lot these days. Also, like humans, we have two eyes, so we have stereo vision, and you could imagine, like, if you close one eye or the other eye, your scene is a bit offset, so you have certain overlapping information between two camera streams, and you could use that to your advantage to process and filter out the noise of each of the individual cameras. So it's known as stereo cameras. Um, and then there is this Xbox 360 or Microsoft Kinect. So if you like to play computer games, you would know about these cameras. So these cameras give you additional information. So you could have RGB information, which is, so you could have the environment observed in color images, but you could also have additional information, which is D, that is the depth of the environment. So you could have a 3D scene understanding where you could have some understanding of depth of the objects from your current field of view as well. So there are different ways of analyzing the environment in terms of vision, and we'll look at the perceptual pipeline at a later lecture. Another sensor which is of interest to me, so I'm currently investigating this sensor, but this is not so well talked about in most of these lectures that you do for mobile robots, but it's an up and coming field, so I'll like to present this to you. So it's called a vibrisal touch sensor. Now, why vibrisal? Vibrisal because if you've seen rats, cats, or dogs, they all have these long hairs protruding out of their face, mostly around the snout area. This is different from the regular facial hair like your beard because they give you touch feedback from the environment. So even a horse, if you see, the horse has whiskers too, and it has a blind spot below its mouth, especially the lower lip. So when it touches something, let's say it's trying to drink water out of the bucket, the whiskers touch the water first, and that's how the horse knows whether it's safe to keep lowering its neck or is there an obstacle, etc. Same way for cats. They have a very coarse vision problem when it comes to objects that are very close to their eye. They literally cannot figure out what's there because they don't have visibility that close to them. That's when they start using their whiskers. The sense of touch tells them, oh, I'm very close to an obstacle. Same way rats. Rats have very coarse visual system. Mostly all rodents do. But rats have a very sophisticated whisking mechanism. Whisking is basically, you say you have whiskers and you're able to move them. So rats have independent control of each of their whiskers. And they use this touch feedback to, interact with the environment, try and figure out where the walls are and stuff, because they mostly move around into dark, damp tunnels and burrows. So this is their most well-developed sensing mechanism. And touch sensing in us as well and in most mammals develop at a very early stage, but we have different kind of applications for that. So for instance, touch sensing on your tongue tells you hot or cold mostly, or the flavors. Touch sensing in your hand, you basically use it to grab things and figure out when the things are slipping in front from your hands. So incipient slip detection. And these are the applications that got transferred to the robots that work in industrial settings as well. But these kind of vibrisal touch sensors are a very niche field at this time, but they're an up and coming sensing modality that allows your robot to move around using the sense of touch. And this is my current research work as well. So the figure that you're seeing here is an early prototype that I developed for a rat-inspired whisker sensor. Of course, the form factor of this was too big, and now we're working on reducing the form factor and making it more compact. And it helps you measure the contact forces. So when you make contact with something, the whiskers bend, and the base of the whisker reports some amount of force that was exerted because of bending, and you use that information to map the amount of bending to the certain distance from the shaft where the contact was made, and that's how you get distance information. The interesting fact about these kind of sensors, especially the way rats work, is the whiskers in rats along the shaft have no feedback. The only feedback that they have is at the base of the shaft, which is where you have the follicle sinal complex, which has a lot of nerve endings. So it's a very, and a lot of blood vessels and stuff. So it is very active in nature. It can gather a lot of information and gives, it responds very quickly. So you could get an understanding of direction, distance, velocity based on your whisking mechanism and where the contact was made. So you could not only just the distance, you could even understand texture, size, shape of the object. So it's very rich in terms of information in that sense. And although it is a touch sensor, so it gives an interpretation that you have to touch something to figure that out. But the cool thing is you can even detect pre-contact forces, which means if there is an airstream coming your way, it would have some vibrations in the whisker and you could detect, oh, the air is blowing my way. Or if it's the air is blowing away from you, then you could use that wind stream direction to chase something. For instance, if you, that's how the sense of smell works, right? So you smell something and then you start chasing it by sniffing it around. So it's kind of like the same principle where you detect flows and you try to go around them. The interesting thing is the pinnipeds, like seals, they also have these kind of whiskers, and they never use them to touch things mostly. Well, sometimes they do, but their more prominent use is when they are swimming in the waters and their prey leaves a wake behind in the water, and they use their whiskers to detect that. So instead of touching their prey, they are mostly detecting pre-contact wakes left behind, and that's how they chase their prey. So this is an interesting modality and a further application of the sense of touch, but in the context of navigation for mobile robots. And since it's my active area of research, I wanted to present that as well. And one word of caution here is that although the word active has been defined in the context of conventional sensors where they emit some energy, people started using the word active whiskers here in the sense because these whiskers are moving. So the way I explain it is these whiskers are motile, which is a common term for neuroscience, where motile means the ability to move, and the antonym would be immotile. So if your sensor is actuated and it's able to move, we just call them motile whiskers and not active whiskers, although that has been used quite often. So just be wary of the different context in which the word active is getting used in the literature. Now, the sense of smell is also very important. So olfaction sensors, which detect some gas concentrations. So these are passive exteroceptive sensors, which could look something like this. And they have stannous oxide as a chemical that is being used as the main component that then reacts with some toxic gases. And depending on the change of concentration of the free ions, free electrons specifically, with how the toxic gases react with the oxide bond, the oxygen in the stannous oxide is what you use to detect the concentration of the gases. And just like the received signal strength principle, you could then use the received gas concentration as a sort of signal strength to navigate the robot around and to figure out where it is and how far the source is, etc. And you could detect different gases. So it could be LPG, propane, carbon monoxide, methane, alcohol, hydrogen, among other things. So think of it similar to your smoke detector alarm in your homes, which we have for safety reasons in most of the countries. The only difference is your smoke detector alarm is fixed in one place in your rooftop, typically. But this is a mobile sensor because it gets mounted on a robot platform, which is able to move around. So, but the working principle is more or less the same. Okay, so we've looked into a lot of different sensors, and different sensors have this notion of performance, right? So how do you define how good or bad a sensor is? So this is known as sensor characterization. And there are various categories which we're going to look into now, which basically you can use to rate your sensor, and so to figure out whether or not your sensor fits the task in which the robot is being deployed, or if you need multiple sensors with different ratings to kind of make your robot deployable in a certain scenario. So first thing that you have to consider is the dynamic range, which is basically if your sensor is able to detect something on the lower end, let's say you're talking about a sonar, which could detect distances between 10 centimeters minimum and 2 meters maximum. This basically means anything that is less than 10 centimeters away from you, you would not be able to detect it. The sensor reports no readings. It's kind of like a blind spot, like the cats have, right? So if the object is too close to them, they don't detect anything with their eyes. And if the object is beyond 2 meters, which is the upper bound that I was talking about, then again you don't report, the sensor doesn't report a reading. So that's kind of like blind spot on the upper bound side. So the dynamic range is the spread of the lower and upper limits of the sensor inputs, and it's typically reported in decibels, where the formula is 10 log max input by min input. Another sensor characteristic that you would be interested in is the resolution. Resolution is the minimum separation you need between two measurable values. I believe most of you might have heard about this term in your high school physics as well, where typically in the context of cameras, we talk about resolution. And this, in other words, it's the smallest change that you could detect in the quantity. So for instance, if there is an audio signal coming in at like 2 decibels, and if I make it to 2.1 decibel, does your ear detect a change in your audio input or not? That is resolution. Like, how much change do I need to have with respect to the previous input for you to be able to detect that, oh, something happened? That's resolution. And the question for you is, do we prefer sensors with high resolution or low resolution? The next sensing characteristic we are looking at is the sampling rate. So the sampling rate or sampling frequency defines the number of samples you are able to take per second for a continuous signal. Think of camera rates per second as an example, FPS, right? So if you're, especially if you're a video content creator and you know your camera as well, not only their aperture, their focal length, but also their FPS is important when you're considering which camera, which lens to use for your given conditions. So for instance, if your camera reports 24 FPS at a certain certain resolution, that means for each second of your video clip, you have 24 distinct still frames that got captured. Okay, that's your sampling rate. Sensitivity basically means an incremental change in the output that is affected by an incremental change in the input. Or in other words, if I change the input ever so slightly, how much of the output would change? Okay, so sensitivity is given as change of output with respect to the change of input. Now, when this sensitivity is a constant, we say that the sensor characteristic is linear, which means there is a linear relationship between input and output. Okay, so you could consider that your output is a scaled version, varies linearly with respect to a constant scalar. But the point is, oftentimes this is desirable. Why is it so? What would happen if the input-output correlationship was non-linear? Are there any challenges do we face? Is there a reason why we want them to be linear? Think about this. It's mostly for practical considerations, and nobody is stopping you from having non-linear relationship. But what are the advantages you see of a linear relationship with respect to non-linear? Just think along those lines. Response time. Now, the sensor should have a fast response time to measure the changes. So let's say a sudden change occurred in the input, and if a sensor takes forever to record and update the output accordingly, that sensor is up to no use, because robots, they have real-time performance constraints. So your sensor needs to cope with certain changes. And typically this is measured with respect to, let's say, if you're from an electronics background, you would know these step signals, right? Or PWMs, if you're seeing the square waves, where you have a zero where it's considered as an off state, and then there is a step size, so after which it's considered as an on state. So when you have applied one step as an input in the increment in the input, then how much time does it take to at least reach 90% of the response to that step in the output side? That's your response time. Now, accuracy, as the name suggests, is very important, because there is a ground truth value to the measurement, and then there is something that your sensor reports. Now, if your measured value is way off, then your sensor is pretty useless. So for instance, if the temperature today is 20 degrees Celsius and my thermometer reports 48 degrees Celsius, that's pointless, because that's not true. But of course, the sensor need not necessarily report 20 degrees Celsius all the time, every time I try to measure it. So there would be some variation. And that is reported by accuracy, which is 1 minus the absolute error divided by the ground truth. So how accurate is my measurement when I'm using a particular sensor? And note that it's talking about absolute error, because sometimes you might offshoot or undershoot. So you want to take into account, you don't want to take into account the positive errors and negative errors, because they might cancel each other out, and you might be falsely led to believe that your sensor is doing amazing, even if it's giving you way off values that are canceling each other out. So it's absolute error. Keep that into mind. Then the precision, often confused with accuracy, is instead the spread of accuracy. So if you have the sensing range and your standard deviation of the measurements, then your precision would be range over the standard deviation, which basically tells you how much spread of your accuracy can you expect when you're using the sensor. And of course, the lower the spread, the more precise your sensor is. Repeatability, as the name suggests, is the deviation of one reading to another when you're taking the readings multiple times, given the sensing conditions do not change. Imagine you're tossing a coin, right? So you keep tossing a coin and you see either heads or tails, and then repeatability would be how often what is the deviation from one reading to another if you just keep tossing a coin, okay? And the question for you is, what's the difference between accuracy and repeatability, if any? And think through this very carefully, because there is a very subtle difference which you might often miss because the terms are slightly misleading. You might think if it's repeatable, it's accurate, or vice versa. But there is a catch here. So give it a thought, look through the definitions again, and then comment down below and explain what is the difference between accuracy and repeatability, if any. Now, we've looked into various interoceptive sensors, various exteroceptive sensors, and various ways of characterizing the sensor's performance, okay? But there are also various challenges when using sensors. And now we're going to look into some of them and try and understand, so every coin has two sides. So in the beginning, we talked about what can sensors do for us and why does a robot need sensors in the first place. But now we're going to see what's the challenge when you're deploying sensors onto a robot. Now, the first two challenges we're going to look into are errors, which are going to be of two kinds. The first is a systematic error. Now, this is deterministic in nature, which is, let's say things like camera distortion. So it's going to happen. You can't do anything about it, but it's deterministic, which means there is no randomness involved when such a sensor systematic error occurs. And the good thing about that is that you could model such errors easily. And if you do sensor calibration, then you can reduce systematic errors. So that's a good and the bad of the systematic errors. Random errors, on the other hand, are non-deterministic in nature, which means you need a probabilistic model to capture the randomness into your errors. And this is typically induced by humans. So for instance, if you are doing an experiment in the controlled settings, which has, let's say, a requirement of using a vacuum chamber, but in one of the experiments, you forgot to tune to suck out the air and there was still some air left. So the vacuum chamber was leaky in some sense, or you forgot to turn on, let's say, if you're doing light intensity measurements, one day you had 4 bulbs on, but the other day you had only 3 of them on, etc. So typically induced by humans, and these are random errors, but you could then capture them in terms of probabilities. And these errors then induce what we call a sensing uncertainty. So let's say you're trying to observe a physical property x of t at a certain time instant t, where your sensor reports an observation y of t. Then the relationship between x and y is given by the following equation, which says y of t equals x of t plus v of t plus eta of t. Now, this is the systematic error. This is the random noise. And as you see, what you observe is a noisy measurement of what it actually needs to be. So another challenge, aside from the fact that it's a noisy observation, is that the sensor cannot know everything there is to know about the environment. It only gets limited observations for you, right? So the uncertainty is of two kinds. with respect to what can be measured, so in terms of the noise, because you have a noisy observation, and with respect to what cannot be measured, because there's a lot of unknown out there in the environment that the sensor cannot measure. So you have a lot of uncertainty. And when you are trying to make some sense of the data that your sensor reported, you have to take into account these kind of things, which is basically, that's why you have to make a full perceptual pipeline, which goes from raw sensor data to some understanding of what that data is reporting and what is it in your environment. So making some heads and tails out of the data. Another challenge is that you have to process the data. And if you come from signal processing background, you would know this as signal conditioning and pre-processing, which includes things like filtering of noisy measurements, removing sporadic measurements like outliers, which is once in a while you might get some outliers in the data which are obviously wrong. So you just discard them in the beginning before you start feeding that data into your perceptual pipeline. So it's like a precursor step of cleaning and conditioning your data and only using the clean version of data for further analysis. Also, as I said before, a lot of these sensors are noisy. So to reduce the impact of noise, you might want to fuse the information across various sensors, which is known as sensor fusion. And we're going to look into this in the coming lectures. And we briefly touched upon that in the IMU, which fuses accelerometer, magnetometer, gyroscopes, where magnetometer is a bit optional, but it might have it. And instead of relying on the drifts and inaccuracies of one of the sensor at a time, it tries to merge the data and then reports the fuse readings for your convenience. So then there is also the problem of rogue sensors. And I haven't seen many of the lectures talk about this thing, but I always talk about this. And I've also discussed things along these lines in my book, where by rogue sensors, analogous to a rogue robot agent, is what I mean is that the sensor has undergone some physical damages, but a robot, of course, does not have an understanding of what went wrong. So imagine things like, okay, the robot is trying to monitor a certain area, and let's say it is given a hard-coded trajectory to go around in a square and keep going around in a square. Forget about the drifts when the robot is moving, etc., and all those challenges. But let's say out of the 4 wheels, one of the wheel encoders or the wheel motors, it got, like, let's say, burnt out or semi-burnt out. So instead of getting full range of motion, it's getting partial range of motion. So, or the wheel is getting dragged along. So instead of spinning in like full capabilities, the robot is now dragging on 3 wheels and dragging one of the wheels together. So that affects the ability of the robot to move around, but the robot doesn't really know, because there is no feedback from the encoder that, hey, I'm broken, or feedback from the motor that, hey, something is burnt out or whatever, right? So that would affect your ability to monitor the area. And even if you're fusing the data with the other sensors, these kind of things may be hard to take into account. But so interoceptive sensors might not report these kind of things. Or another possible damage that might occur is, let's say you have, let's remember the grid of Abraham Lincoln's picture that we were talking about, and some of these pixels might just go dead. Physical damage to the camera for whatever reason. Sometimes you have it on your mobile screen where you have a dead pixel. So that could happen. Or imagine deploying a robot into an environment that has, let's say, some suspended particulates, maybe some sticky smog particles or some ashes that might get stuck to the camera lens. And if the environment is caustic or dangerous for a human to enter, you might not even be able to clean it up. So you get some occlusions in the field of view, and the robot is just kind of like half blind in that scenario. Also, a very extreme case could be the case of hacked sensors. Maybe you're using some Wi-Fi network and somebody hacked into the Wi-Fi and hacked your sensors, and for whatever reason that they changed the sensor data, etc. So all of this affects the robustness of deployment, and the sensors go haywire. That's why I call them rogue sensors. These are some of the challenges you need to take into account when you're deploying the sensors, and depending on how safe and robust you want the robot to be in these kind of scenarios. And in case if you have a multi-robot team, like, do you want the team to be agile in the sense that no matter if there is a hacked sensor, damaged physical hardware for one or multiple robots? Does the team compensate for the others, and so on? So these are the considerations to take into account. All right. So with that, we wrap up today's lecture, in which we talked about various kinds of sensors, what the sensors can do, some overview of the working principles, how do you characterize the performance of a sensor, various kind of caveats and some words of caution, some unconventional sensors as well, so vibrisal sensors. If you want to learn more about them, feel free to leave a comment for me in the comment section below. I'd be happy to chat more about those kind of things. And then we looked into various challenges of sensing, both in terms of a fully working sensor and the noise and the uncertainty that exists with it because of the things that it can and cannot measure, and also in terms of rogue sensors and the amount of extra effort you need to put in to clean up the data and make some sense of the data if you're using sensors for mobile robot navigation. All right, with that, I wrap up this lecture. Be sure to like, share, and subscribe to my channel, and share this video with other fellow learners who might benefit and who are beginners in robotics and want to learn more about it. And with that, I will see you next time. So be sure to hit the bell icon and turn the notifications on so that you're notified as soon as the next lecture goes live. All right, see you next time. Take care.